All right, so what we're going to do today is we're going to try to review some of the things we discussed in the previous lecture regarding ordinary differential equations and initial value problems, and then do some new topics, hopefully nothing major. Okay, so I remind you that the major textbook that I am following is the book by Boyce and Di Prima, okay? And the material for first order ODES is on chapters 1 and 2. But the notes and the slides cover most of it. But you know, there is a lot of information in that book that is very qualitative and very useful. Okay, so let me start with a trivial example that we discussed about these direction fields, to be sure again that those who were not here last Friday, they know what we're talking. So here is a simple ordinary differential equation. V prime is dv over dt, and this equation actually corresponds to a falling ball in a gravity with some air resistance. Okay, so m times the acceleration is the mass minus some resistance, and what you see is what is called the direction field. It's basically a qualitative way to understand the solutions of the ordinary differential equation without actually having to solve it. And the way you compute this is, so you plot, this is the velocity v, all right? So it's the dependent variable in the ordinary differential equation, and this is time t, all right? So the independent variable is t here. So what you do is, you go and you compute the slope of the velocity. This is what it is, right? It's the slope of the velocity for different values of the velocity v. So you take different values of v, so you take v equal to 0, and you can see you have a velocity, the slope is 9.8, okay? So you draw this, and you notice here the slope is only a function of v, so it's going to be constant for all t, okay? Then you go to v equal 20, v equal 40, etc. And these arrows have a lot of information because first they point to you to an equilibrium state, which is 9.8 divided by 0.2, all right? So it's whatever that is, okay? And you can see that straight line, and then you can take advantage of these arrows and effectively draw a solution if you know where you start. So for example, if you know some initial condition that at time 0, your velocity is 0, you can actually follow these arrows and you can see that the solution is going to go asymptotically to the equilibrium state. Or if the initial velocity is 80, you can just follow the slopes and you will go again all the way down to the equilibrium state. Again, these arrows are a qualitative way to draw the solutions on a piece of a napkin, for example. So when you eat pizza and you want to think about the solutions of differential equations, you can do this. Now, of course, if you can solve the differential equation, that's the best, right? It contains all the information, but if you cannot, you should be able to at least do this. And we will do a lot of these plots in this course, okay? So be sure by the first homework you know how to do them. Okay, so this is another problem, basically of the same structure. This is the population of mice, okay? And there was some growth and some death rates there. And so dp over dt was given by this equation. And again, there was some steady state, some equilibrium state given by that horizontal line. But you notice the behavior here is different from the falling ball in gravity, because here, if you start with initial states that they're below the equilibrium state, so below this number that is 900, you can see you will, basically you will go to minus infinity, okay? This decreases. If you start above that, the population of the mice increases exponentially, okay? So again, the equation looks the same, but because of the right-hand side, you do get two different things happening. So let me go to slide 19 and put up the very general differential equation. So we discussed about equations that we gave the definition of what we call linear equations. We discussed the order of equations. So this is an ordinary differential equation where the variable is y. It's a function of t. And it's a function of t. And it's an nth order differential equation. And what we have done is we isolated the nth derivative on the left-hand side. And we plugged in everything on the right-hand side. So phi is a solution basically where it satisfies this equation at some interval, not just at one point, but at some open interval, in time t. And if this function comes to be linear in the arguments, then we call this a linear ordinary differential equation. And I remind you, linear means that it's a combination of these y's that you see there, but the coefficients can be functions of time. Okay? Still linear. All right? But you cannot have terms like y squared times y prime or y times y prime. Those are nonlinear terms. Okay. I need to do lots of jumping today if we're going to do anything significant. So let me go to slide 20. I am going to actually discuss about these things on Wednesday. But obviously, if I give you an ordinary differential equation, you really need to know, can I find a solution? If I can, is the solution unique? And then, of course, how do you actually find one, even in cases that the equation is nonlinear? So we're going to have to discuss about this on Wednesday. Okay. So the equations that we discussed in the lecture on Friday, they were fitting basically in this simple form, all right? dy over dx equal f of x and y. And in case you get confused, let me just say that the independent variable in some slides is shown as x, in some slides is shown as t. They are all of them ordinary differential equations. If you see t, then the name I use for this type of equations is basically initial value problems, because we have to specify y at time 0, so we call them initial value problems. Now, if it happens that the equation doesn't have this form, it's always a good idea to actually put it in that form. So if you have something like that, x to the minus 3 y prime, divide by x to the minus 3 to put it on this form. So we will use this as a reference format for these ordinary differential equations. So let me do two trivial examples. So this is a simple ODE that models exponential growth. Actually, we're going to use this population growth problem in different settings and in different forms of the differential equation, hopefully today or on Wednesday if we don't finish it today. But here you have a pure exponential growth. Okay, y prime equals some constant times y. So obviously the solution, starting from the value 0.2 at time 0, right, is e to the 0.2 times t. Okay, and these are different solutions starting from different initial conditions. So this is pure exponential growth, all right, and the differential equation is very simple. Y prime equal 0.2 of y, or generally speaking, y prime equal to some constant times y, where that constant here is positive. On the next slide, you have an exponential decay. The equation looks, if I can see the equation somewhere, looks the same, except that the coefficient is negative, all right? So this is an exponential decay. So this, you start from different values of y, and asymptotically you go basically to 0. Now this is sort of a very common behavior, right? Lots of systems, they will either grow exponentially or they will decay. So being able to immediately see the solution for this type of problems is very helpful. Okay, so let me talk about the initial value problem. So I'm only interested in the equation written on the bottom. So effectively, this is our standard problem. You can think of x being the time. So this is a first order ordinary differential equation. We provide some initial condition. And again, I'm going to discuss on Wednesday when that problem has a solution, and if it does, when that solution is unique. So let me solve some trivial problems that we have seen. So I'm going to put all of these things up. So this is the population of the mice that we have seen, the standard example. There is really nothing here to know about solving ordinary differential equations. You can just rely on calculus. So P prime is dP over dt, all right? And so you can actually separate dP over, I mean, if you write it, you know, if you put the 0.5 outside and the rest inside parentheses, you can write this as dP over P minus 900 equal 0.5 dt, and you can integrate the left and the right-hand side separately, right? So this is what we call a trivial example of separable equation. And you do get a solution, actually, that literally looks like there is some growth there that is exponential. And it's not surprised because you can see that equation there. That's the exponential growth that we have seen, okay? And then there is a constant term 900 that obviously imply maybe some equilibrium state, okay? And you can see here when P prime is equal to 0, when P is equal to 900. Now, the behavior of this equation, can you tell me how it will behave? How it will look if we try to plot it? What parameters do they define this, you know, the nature of this equation, the solution? I mean, the exponent has already been defined. So e to the minus 0.5t is exponential growth. But what it will tell me if it is exponential growth to plus infinity or minus infinity? What will define the nature of this solution? What's the only parameter that we have not specified yet? K. And K will be specified through an initial condition. All right? So if the initial condition, you remember, it was above 900, all right? So the population P will grow exponentially like that. If it is below 900, it will basically decrease, okay? And everything is defined through this parameter K. All right, there's nothing new, and this is the direction field that we have seen before, okay? And what I will ask you actually, even in your homework, when it says plot the direction field and also the solution, you have to do this on the same plot, not separately, okay? So what you see here is the direction field, including the equilibrium state, and at the same time, you see the solution of the ordinary differential equation of the initial value problem for some initial condition P of 0 equal to 850, okay? So can you see now, you know, literally if you solve, if you put P of 0 equal to 850, all right? So for t equal to 0, you get a K contribution here. So 900 plus K equal 850. So K is minus 50. So this is the solution. But can you appreciate that if you have this direction field, more or less you're not surprised that the solution looks like that? Right? Okay, I mean, you will not be able to do it precisely, but basically the direction field tells you exactly what is going on. And this is the general form of this type of separable equation. So I'm going to write a very general equation, y prime equal a times y minus b, all right? And generally, a can be positive, can be negative, and the same for b, but we have it in this form. And again, this is a separable equation. You can write this dy over y minus b over a times a dt. So you put a outside the parenthesis here like that, okay? You solve it, and if you put the initial conditions at time 0 to be y of 0 to be y0, you get the solution that you see on the bottom, okay? So this is how the solution for this equation looks for any time t. I don't know if there is a plot, okay? But obviously, if somebody asks you to discuss the nature of the solutions, what you will need to know is, you will need to know, is that exponent positive or negative? And if it is positive or negative, is the coefficient in front positive or negative? So that way you will know if it goes to plus infinity or minus infinity. So obviously everything depends on not only on the coefficient A, but also if the initial condition is higher or less than B over A. And that's why the B over A, it's sort of the equilibrium state that defines what's going on. Different things are happening above and below B over A, and the equation contains all that information. All right, so I don't need to do this example. And I remind you, and actually I'm going to devote more time on this. So if you want to get basically the equation for the solution for this ODEs for arbitrary initial conditions, and you want to do it for any ODE, basically you have to use something like the Euler method that we discussed on Friday. And I'm going to tell you a little bit why the Euler method is not, even though it's the reference method for solving ODEs, why it is not accurate in many problems, okay? But let me just throw this example for this particular ODE. And this example is interesting because the right-hand side not only contains y, but also contains x. So when you evaluate the slopes in y and x, right, so you're going to have to take different combinations of y and x and evaluate y plus x. And the errors look like that. And look why this is very interesting, right? So you can see three solutions of this ODE for three different initial conditions. But observe that sort of this straight line, all right, this straight line separates the nature of the solutions. I mean, everything, if you start on the left-hand side of that line, everything seems to be going down to, you know, with more or less constant rate to minus infinity, but the solutions up here, they seem to turn and go up to plus infinity, okay? So that simple x there is sufficient to change the nature of the solutions. And let me remind you just what was the Euler method. So let me just put only one equation. So the Euler method effectively was an explicit method to advance an approximation to the solution from one step to another. So if you know the solution, let's say at initial time x0, you know the solution is y0, you evaluate the slope using your initial solution, and then you approximate so the slope with f of x0, y0, and y1 becomes y0 plus a delta t step, right? Which we call it x here times f of x0, y0. And I am going to show you lots of these things in, if not today, on Wednesday, to discuss some of the pathologies of this method. But this is more or less how the Euler method looks like. This curved line is, let's say, the exact solution. So what you do is you know the solution at x0 is y0. You want to find the solution at x1, right? The actual solution is there. So you want to approximate it, and that's the approximation. So what you do is you approximate the slope, evaluate it at x0, y0. So that's this straight line. And effectively, at x1, your new approximation is that middle point that you see up there. So obviously, there is a big error here, right? And what I'm going to show you actually, if not today, on Wednesday, is you can appreciate that in the next step, you will use x1 and y1 to calculate the slope at this point so you can go to x2, y2. But look at this point. This point is way off the exact solution. So you're going to be approximating the slope to the actual solution using something that is not in the actual curve of the solution. So as you keep going, right, this arrow will keep growing. So after a few time steps, basically this thing may completely diverge, okay? We're not going to give you any expressions for the error in this class, but I have tables to show you exactly why this may get you in trouble. But remember, a method that may sound not to be correct for many problems, for many nonlinear problems in particularly, is still a fantastic method because everything else that solves the problem is based on the Euler method. All right, something simple. The first idea is the most important. The rest are incremental steps, okay? So the Euler method is something you need to know. So when somebody asks you what you will do, and you say, I'm going to start with the Euler method. Okay, so what slide we are? 53. So let me go to slide 55. Okay. I am not going to do anything specific to this slide, but if you look at the equation on the top, if you have an ordinary differential equation that has some coefficient of y times y prime equal f of x, you can immediately see, right, that this equation is separable because everything on the left is a function of y, everything on the right is a function of x. So actually, you can find a solution, at least implicitly, by integrating in y on the left-hand side and integrating in x on the right-hand side. And so this will be sort of the easiest possible case of a separable equation. And I don't want to do this example because it's simple and you guys, you will read it. So let me take an equation that doesn't look separable, but maybe it is separable if you think, for a few minutes. So my equation looks like y prime is some function of y and x. All right, so obviously f can be anything. All right, so really this is a nonlinear equation because if f is quadratic, right, it's like I'm going to be getting y over x squared. So obviously that's a nonlinear equation. Any idea on how to actually make this equation separable without looking at your notes and your computers? After you read all the slides in the weekend to entertain yourselves? So if you have an equation like that, how can you make this equation separable? It doesn't look to be separable, right? It can be, you can see here, it's a nonlinear equation. Okay, it can be a function, can be a sign. So how can you solve it? So the idea here is we're going to define a new function, u, that is y over x. All right, that would be an obvious substitution. So we're going to change variables, and we will go from y to u. So this is my definition. I'm going to define u to be y over x. So if you take derivatives, obviously u is going to be a function of x, right? Y is a function of x, so u is a function of x. So if I'm going to take derivatives of this, y prime will be u prime times x plus u. We agree? And if you plug in this in the original equation, you're going to have u prime times x plus u equal f. You remember the differential equation is f of y over x, which is f of u. And that equation actually is now separable. Can you see that? Right? So a little trick, right? A little trick, and it takes an equation that doesn't look to be separable. It's highly nonlinear. By defining u to be y over x, you get something like that. So obviously, your problem now will be to integrate this to get u. And obviously, when you integrate the left and the right-hand side, this integration, if you can do it exactly, will be an implicit integration, right? You will get something that involves a function of u. All right? But if you have even implicitly u, then using the definition of u, you can say y now is x times u, and you're done. Okay? And so something that doesn't look separable, it's actually easy to handle. So let me take this equation, okay, as another example. dy over dx equal x squared over 1 minus y squared. Obviously, this equation is separable, all right? So it's not a linear equation, but it's no big deal. If I put 1 minus y squared together with dy, x squared together with dx, you can integrate on the left and the right-hand sides. And can you appreciate that the solution you get is actually implicit? Implicit means you don't have something that says y equal to this. You have y cubed minus 3y equal minus x cubed plus a constant. All right? Do you know how to solve cubic equations? Can be nasty. All right? Can be nasty, actually, solving a cubic equation. So in this case, all right, when we say we have an implicit solution, and unless I ask you, in the homework, you can just leave the solution like that, unless it's a quadratic, all right? So without putting yet any initial conditions, this is how the solution looks like. But don't be scared, right? It's an implicit equation. So, you know, you are going to have to solve this with some numerical means to compute for each x what y is. And here is how the solution looks like. And you notice, because this equation is not linear, there is a lot of interesting things happening in this equation, right? So you can see the direction field, how it goes. And these curves that you see here are some of the solutions of this nonlinear equation for different initial conditions. And obviously, you can appreciate that you know, asymptotically seems all the solutions are approaching this line here. Okay, so in essence, this is you know, at the infinity, this is where you go, and all the solutions emanate from this side. Okay, and here is another equation. Okay, that's also easy to solve implicitly, but this equation is a little bit nicer because if you notice, when you separate y and x, the equation that you get is quadratic, and you know how to solve quadratic equations, right? So here is the actual explicit form of the solution by solving the quadratic equation. Now notice, because a quadratic equation has two solutions, do you keep both of them? What defines which solution is the correct one? What will define if you keep the plus or the minus? Because there's no way that you can have two solutions here. Initial conditions, all right? So basically, you will, if I give you, let's say, at a given x what y is, you will plug into both the solution with the plus sign and the minus and see which one can actually take care of this boundary, of this initial condition. So if the initial condition is y of 0 equal to minus 1, this is how the explicit solution will look like, all right? Must be somewhere written there. That's how the solution will look like, the one with the minus sign. And this is how the direction field and the solution of this ordinary differential equation will look like. There is actually, you know, when you know, if you have something like that in your homework, take 10 minutes and start talking about what you observed, right? Why the solution looks like that. So in my initial condition is y of 0 equal to minus 1. And you can see that black line there. That's the solution with that initial condition. And I trust at that point where the black line intersects the y-axis is obviously the point x equal to 0 and y equal to minus 1. Can you see that? Okay. And look something else, right? Can you observe, what do you think is the slope of that black line of the solution corresponding to this? What is the slope at x equal to minus 2 and y? What is the slope of the actual solution, that black line, at x equal minus 2 and y? You can also consult the original equation. If you look at this equation here, the exact solution, at x equal to minus 2, what is y? So minus 2, this will become x cubed will become minus 8. And this will become plus 8, they cancel. Minus 2 will become minus 4 plus 4 cancels, so y is equal to 1. And what happens at y equal to 1? How much is the slope of the solution at y equal to 1? It's infinite, okay? So basically, you can see that x minus 2, the solution, basically that is the limited point, and then the solution starts curving to the right, okay? So when you plot solutions, you know, be sure that you include the correct interval, okay? The correct interval where the solution is being defined. So here, basically, this solution is defined from minus 2 to plus infinity, okay? From minus 2 to plus infinity, okay? And this is how the solution looks like if you want to see it in a nicer plot, from minus 2 to plus infinity. All right. What slide is that? 67. We're done with page 1 of what we need to do today. Here is another equation, all right? There's a lot of examples in the notes, but if you look at this, right, it's also separable, okay? And if you integrate y and x separately, you get this. This equation is a fourth order equation in y, okay? And if you put, let's say, some initial conditions, y of 0 equal to 1, you can calculate the constant of integration, and you get something like that, all right? And assuming that you can solve this equation, if you cannot solve it exactly, you can certainly solve this numerically. And that's actually why solving polynomial equations, right, or equations of this form for x, it's sort of a standard exercise when you take a numerical analysis course, but really comes very handy for differential equations. You know, I trust that both Mathematica and MATLAB will actually calculate for you exactly the solutions to this equation, okay? But why I wanted to plot you, to show you this equation is because look at this interesting, wonderful plot of the solution. All right, so my equation looks like that. And look how nice the solution looks like. All right? Can you tell me, so there is, you know, there are some points there, these two dots, right, correspond to points where the slope basically becomes infinite. Can you compute for me those points? How do you compute those points where the solution becomes infinite? And I mean, I can be looking directly down there. So those points correspond to what values of y? So when 4 plus y cubed equal to 0, all right, you can see basically these lines become vertical, okay, at those points. And 4 plus y cubed equal to 0 means you have to compute the cubic roots of minus 4. Okay? And when you do that, actually, you can verify, and that everything is in the slides, that at these points, that they're plus, minus, you know, so y is like that. And you actually compute this for this particular solution that passes from the point 0, 2. So that's my initial condition. Actually, you know, I'm sort of color blind, but now I can see, actually. Can you see this? There's one line there that is a red line. Is it a red line that goes all the way around? Okay, it's like the third line from the top, okay? So that's my solution for this initial condition. It passes from this point. At x equals 0, it passes from the point, is that 2? No, wrong. So the initial condition has to be, you know what, at x equals 0, y equal to 1. Okay? So for x equal to 0, y equal to 1, and you can see at x, for that solution, for x plus minus 2, y takes, no, I'm sorry, x equal plus minus this 3.34, the value of y gives you a slope that goes to infinity. Okay? But again, two different nature of solutions for the various separable equations that we have seen in this lecture. Okay, 69. So let's jump to this example 75. And I know in principle we did this on the lecture on Friday. So let me go rapidly through this example. So we want to solve the equation on the top, okay? And we are going to use what is called, this concept is called the integrating factor, okay? So the integrating factor is somehow, if we multiply this equation with some function of t to be specified, this equation may become easier to solve. So let's figure out what this mu of t should be. So I multiply this equation with mu of t, left and right hand side. And now you concentrate on the left hand side. And I want to make the left hand side as the derivative of mu times y. All right? So I want to make the left hand side to be the derivative of mu times y. And to be able to do this correctly, the derivative of mu times y is mu times dy over dt, which is what I have, plus d mu over dt times y. So d mu over dt has to be equal to, d mu over dt has to be equal to 1/2 mu, thank you. And 1/2 mu means that mu has to be e to the t over 2. And really, the integrating factor here is not unique, right? So we don't really bother about constants of integration and the like. So mu equal e to the t over 2. So actually, look at this. If you multiply by e to the t over 2, indeed, okay, then this becomes d over dt of e to the t over 2y. So you can actually integrate the y and the t separately. And there is the solution, and you're done. And if you want to plot it, this is how it looks like. Okay? And I have the arbitrary constant of integration there, but this is the method of this integrating factor, okay? That if it works, it basically gives you the solution right away with very little for you to have to worry. So let me do this in general, because the equation that you see on the bottom, I want you to actually remember it, because when we do other methods in this course, including the Laplace transform and things like that, even when we discuss the solution of these equations to impulse forces, this equation is going to come up in different forms, right? But more or less, all of them are the same. So let me review this solution to this general equation, y prime plus ay equals g of t. G of t is any function, okay? So multiply by mu, all right? So can you tell me now, what do you like the derivative of mu to be equal to make this easy? So d mu over dt has to be equal to, on the left-hand side, remember, we need to get d over dt of mu times y. So what we would like d mu over dt to be equal to? D mu over dt equal to a times mu, which means it's going to be e to the what power? E to the at, okay? So remember, mu has to be e to the at, so mu equal to the at is like that, all right? So the left-hand side will become the derivative of this. The right-hand side, okay, is e to the at times g, so I can integrate on y, I can integrate on t, and divide by e to the at, and this is the wonderful final solution to my ordinary differential equation, okay? Sometimes inside this integral here, all right, when you integrate this, you don't actually put t explicitly because you don't want to confuse it with the independent variable. You can put a dummy variable inside the integration. So instead of having e to the at g of t dt, you can write down e to the aes times g of s ds, right? some other dummy variable, and then you can even change the limits of the integration here from 0 to t. So this solution here is extremely powerful, and I want you to actually look carefully. It has two components. Look at this second component. From where is c e to the minus at coming from? Look at this and tell me, where is c e to the minus at coming from? E to the minus at. From where is it coming? That's the solution of what problem? How do we call that problem? I mean, I have, this is a linear equation, right? So I have two contributions. This contribution comes from where? From what problem? Y prime plus a y equal to 0, and that, how do we call that problem? You remember solving ax equal b? How do we call the problem ax equal to 0? The null space, or more general, I mean, we can call it the null space solution here as well, would be the homogeneous problem, right? So e to the minus at gives me the solution to the homogeneous problem. And what is this thing here, this big e to the minus at and then this integral? It is the solution, one solution to what problem? It's the particular solution, all right? Exactly the way we have done it with linear algebra. And actually, you can verify that this solution is the solution to the particular problem, because if you take derivatives with respect to, if you take y prime, all right, of the first term alone, right, you're going to have the derivative of e to the minus t times this integral, and then you're going to have e to the minus t times the derivative of the integral, which will be e to the at times g, all right, and that will give you a g term there, okay? Please verify, all right? We derive it, but verify that the first term is the solution to a particular solution to our non-homogeneous problem. So again, a solution is written as a particular solution to the non-homogeneous problem plus the null space solution, exactly the way we have done with linear algebra. And I really want you to remember this equation, because we will use it very often in very different settings. And even for second order okay, we will come up with some similar form. So please remember how this equation looks like. And if you take, one particular application of this, all right? So if your equation looks like this, right, you can use the general form of the equation I have. So in this case, a is minus 2. All right, so I plug in here e to the 2t and e to the minus 2t. G is 4 minus t. If you do the integration, this is the general solution that you get for this ordinary differential equation. And actually, you can plot this with the direction field as well. And you get, so this is our general equation, okay? And you get a field that looks to be separated around this line. Can you tell me what is this equation of this line and from where it comes? I mean, when you see a line right there, it's a particular solution of this for some initial condition of this ordinary differential equation. Can you tell me this line is the solution for what initial condition, you think? For what initial condition? For t equal to 0, all right, if c equal to 0 here, all right, what will be the value of y? Minus 7 over 4. All right? So if the initial condition is minus 7 over 4, you can immediately see that this coefficient c is 0, and the solution is minus 7 over 4 plus 1/2 t. It's a straight line, right? So again, if the initial solution is minus 7 over 4, then the solution of the ODE is minus 7 over 4 plus 1/2 t. And you can see that this line separates basically the direction field in one that grows exponentially if the initial conditions are above minus 7 over 4, positively exponentially, right? And another one that decreases I mean, increase exponentially, but in the negative direction. All right, so that's a nice way to see this, the solution to this problem. There is really nothing new in this equation, so I just gave you, so for the equation that you see again on the top, all right, this is the general solution using this integrating factor mu of t, where mu of t is e to the integral of p of t dt. Where did the integral come here? So I don't have to repeat things. Where did the integral, why is mu equal to e to this integral? Remember, you told me that I am going to use that the derivative of mu with respect to t has to be equal to what? The derivative of mu with respect to t to make this method work has to be equal to p. So if you have d mu over dt equal to p, what is mu? No, I'm sorry. The mu over dt has to be not equal to p, it has to be equal to what? P times mu, right? Not equal to p, p times mu. So you're going to get basically the log of mu equal to the integral of p dt. So mu will be to the integral of p dt. So this is the general solution using this integrating factor, all right? For the case where the coefficient is not constant, but it is a function. It's a function of t. Okay, so let me actually, I'm going to jump and go to this nice equation. Okay, so let me put everything up. All right, so we're going to extend this idea of integrating factors to a little bit more complicated scenario. So let's suppose we have a first order ordinary equation that looks like that. M, a function of x and y, plus n, a function of x and y, times y prime, equal to 0. So in principle, actually, a lot of times in textbooks, if you write y prime as dy over dx, this equation appears as in the form m times dx plus n times dy equal to 0. Can you see that? M times dx plus n times dy equal to 0. If you write y prime as dy over dx. So I mean, I know I told you before, right, we should have y prime by itself, you know, not multiplied by this coefficient. But here, for this particular discussion of integrating factors, we would like to keep this equation as is. So let's see how this method works. Suppose, out of nowhere, that you can find me a function psi of x and y, so that the x derivative of psi is equal to m, and the y derivative of psi is equal to n. And you notice there is a suppose there, right? If somehow you can find a psi function that its x derivative is equal to mu and its y is equal to n, then let's see, let's plug in this psi values inside the differential equation. So what is m? Is del psi del x. What is n? Is del psi del y times dy dx. Will you agree? Look at this here. This is a miracle there. M plus n times y prime appears to be equal to that right-hand side there. Will you agree? So remember, psi is a function of x and y. And y is my main unknown, right, which is some function of x. That's the solution of the differential equation, and I call the solution phi of x. Y is what I want to compute. I call it phi of x. Look at this. Is this equal to that? Is this equal to that? How do you differentiate a function of x and y with respect to x? You will first take the derivative with respect to x, and then you will add the derivative with respect to y times the derivative of y with respect to x. Isn't it? From calculus. Right? Now, remember my differential equation is that m plus n times y prime equal to 0. So if this is equal to 0, what is the solution then of the differential equation? What is the solution of the differential equation? That psi is equal to a constant. And if psi is equal to a constant, this equation, because y is my unknown, this equation defines the solution of the differential equation, but implicitly. Because y may turn out to be a sine function, a cosine, who knows what, right? But implicitly, I have the solution of the differential equation using this very nice method. Okay? So again, this leads to an exact solution to the problem. If there is a function psi, so that its derivative with respect to x is m, and its derivative with respect to y is equal to n. And the question is, can you actually guarantee that there is such a thing, and under what conditions? And the answer is very simple. And actually, let me go directly on this because it's 11:21. Remember, we set m to be the derivative of psi with respect to x, and the derivative n to be the derivative of psi with respect to y. Now, if psi is a function of x and y, and it's a continuous function, the second derivative of psi with respect to x and y is the same as the second derivative of psi with respect to y and x. You can change the order. So if effectively the derivative of m with respect to y and the derivative of n with respect to x are equal, then there is some function psi that does the job. Okay? So this is what the first thing you need to do. The derivative of m with respect to the other variable y and the derivative of n with respect to the other variable x have to be equal. And that comes basically from the fact that the second derivative with respect to x and y is the same as the second derivative with respect to y and x. And let me just throw one example. If this is your equation, you can actually verify that the derivative of m with respect to y is the same as the derivative of n with respect to x. And you can basically, as we said, the derivative of psi with respect to x will be m, of psi with respect to y will be n. And then what you have to do is take the first equation, integrate it in x to compute psi, and then whatever result you get, differentiate with respect to y and set it equal to n. And hopefully this will give you the function psi as a function of x and y. And the answer is actually on the slides before the time hits me. There is the function that you see here. Let me give you the final answer. Here's the answer. Y sine of x plus x squared e to the y minus y plus some constant. That's the function psi. And when this function is equal to 0, it gives you implicitly the solution y. Obviously, there is no way you can solve this by hand, right? So the solution is defined implicitly. But if you have a computer, for every x, you can compute what is the y that satisfies this equation for some initial condition.